Please take a seat, everybody. Okay, thank you very much for coming to this afternoon's session where we have a few very interesting physics talks. So my name is Jiehang Zhang. I'm a professor here at BIMSA, and I will be chairing this session today. So we have the first speaker, Professor Zohar Komargodski, from Simon Center for Geometry and Physics, New York, and also Stony Brook University. So he is an expert in quantum field theories, conformal symmetry, supersymmetry, quantum gravity, and particle physics phenomenology.
Oh, wow.
And he will tell us about symmetries in gauge theories and their applications. Let's welcome.
Thank you very much. Awesome to be here. I will give a review about the recent role that topology, and some discrete mathematics played in the field of many-body physics and quantum field theory. So the plan of this talk is that I'll start from maybe a half an hour of a very simple pedagogical example that shows the main ideas of how some simple discrete mathematics and topology can teach you something somewhat surprising even about very simple toy models. And then we will graduate to gauge theories and see the implications for gauge theories and their phase diagram. So we'll make some new predictions about gauge theories at zero temperature and also at finite temperature. Also, if there are any questions, just stop me with any remarks or comments. So the most important problems in many-body physics in equilibrium involve strong coupling. Of course, the systems which are weakly coupled are easy to solve, and the systems which are strongly coupled include Planck scale physics, confinement in Yang-Mills theory, high temperature superconductivity, conformal field theories in conformal field theories above 1+1 dimensions, and more general magnetism problems. Spin liquid phases are extremely strongly coupled 2+1 dimensional systems. They're very interesting in for a lot of applications, etc., etc. So when you encounter problems in many-body physics that are afflicted by strong coupling, you can of course do a lot of numerics, and there is a lot. I'll mention maybe some results from numerics at the end, but another approach is to try to develop exact results. And exact results are difficult to come by, but when they exist, they're very strong, they are rigorous, and they're very robust. So I'll emphasize this attempt to develop tools which are exact and apply even in strongly coupled systems. And there are many applications of these methods, but I'll just focus on Yang-Mills theory because those applications are perhaps some of the earliest. And this is a review talk of one of the earliest applications that we found with Gayotto, Kapustin, and Seiberg. And so that's what I'll emphasize. Related work is with Ryan Thorngren, Sharon, Sheena and Zhou, Tim Suleiman Pasic, Mithat Unsal, Jaume Gomes, and many others. So this field is very, very, very big. The field where people try to use topology to constrain many-body systems, either in the continuum or on the lattice. In fact, I could have given this whole talk today on the lattice because everything I'm going to say about the continuum Yang-Mills theory holds exactly on the lattice as well. Okay, so the first problem as a warm-up is that we'll study something that you may have seen in undergrad, which is just a particle moving on a circle, and there is a magnetic flux, a Aharonov-Bohm flux, at the center of the circle. This is a very familiar problem from the 1950s due to Aharonov and Bohm, and even before Dirac, of course, encountered that problem when he studied the monopoles. So this is the warm-up problem that we'll go through. So the classical Lagrangian is of course just a kinetic term on the ring, and there is some potential on the ring. I'll just assume that the potential is some periodic function in general, but for the sake of the warm-up, let's assume that it's vanishing, so there is no potential. So classically, the particle just spins around the ring with some frequency omega, and then the energy is a half of this frequency squared. So that's the end of the classical physics discussion of this problem. And of course, famously, classical physics does not see that there is an Aronoff bomb solenoid at the center of the ring. But quantum mechanically, uh, this Aronoff bomb solenoid becomes visible through the fact that the wave function is not exactly periodic, but it's periodic up a phase. And the phase happens to exactly coincide with the magnetic flux, modulo 1, modulo 2 pi, I'm sorry. Okay. So the quantum Lagrangian, you could think about it in several ways. One way that I prefer to think about it is that the the classical Lagrangian has a total derivative term, and just as a classical physicist, it doesn't influence the equations of motion or the action. But quantum mechanically, since we have to sum over all the possible histories, this total derivative term becomes interesting because when you evolve in time, the particle could have gone around the circle 7 times, and that would have added some phase to the path integral. So you could say that classically and quantum mechanically there is no difference, it's just that the total derivative term quantum mechanically is important, while classically it's not important. Okay, so this is what I just said. This total derivative term becomes important in quantum mechanics. And also, I'll just emphasize again that as Aronoff and Bohm and Dirac realized, this parameter theta is periodic because if theta is shifted by 2 pi, there is no difference. It's the same differential equation as far as the equations of motion are concerned. And also, as far as the path integral is concerned, the phase that you get from these histories that go around the circle n times is going to be exactly the same if you shift theta by 2 pi, because this phase is just 1. So theta is a periodic parameter that classical physicists don't see, but quantum physicists do see, modulo 2 pi. So the solution of this problem is, of course, very familiar. This total derivative changes the conjugate canonical momentum in this fashion. Then the Hamiltonian is given by the conjugate momentum minus a constant. The wave functions, which are eigenstates, are just exponentials in Q, like that. And the energy levels are shifted by the Aronoff bound flux n minus theta over 2 pi squared. Let's just plot it. Okay. So in particular, the energy levels are periodic. The full set of energy levels is periodic under shifting theta by 2 pi. And that's here, maybe in the picture, it's more clear. So if you follow an individual energy level, it's not periodic under shifting in 2 pi. But if you look at the full set of energy levels, it is periodic under shifting in 2 pi. Are there any questions about this quick summary of the Aronoff-Bohm problem? Okay. So you can ask, what do we mean? This will be important for the future. What do we mathematically mean when we say that theta and theta plus 2 pi are the same? We can say that the set of energy levels is the same, but that's not enough for two quantum systems to be the same. For two quantum systems to be the same, you have to find the change of variables. So the mathematical meaning of that is that there must be a similarity transformation of the Hamiltonian, which takes theta to theta plus 2 pi. So if you found a similarity transformation, then you can really declare that the theories are identical. And indeed, there is a unitary operator, which is the exponential of the position. It's a well-defined unitary operator because the position on the circle is defined modulo 2 pi, and therefore the exponent of IQ is well-defined. So using this unitary operator, if you go through the small exercise of conjugating the Hamiltonian by this unitary operator, you'll see that it just shifts theta by 2 pi. So if you take this Hamiltonian here, and you conjugate it with e to the iq from the left and the right, you'll see that the new Hamiltonian has pi q minus 1 minus theta over 2 pi. So that's the mathematical meaning of saying that theta is defined modulo 2 pi. There is a similarity transformation. Okay, a very interesting case that will be the focus of some of the discussion today is when the flux is exactly a half integer mod 2 pi. So pi, when the flux is pi. if you look at this picture from before, you'll see that at the theta equals pi, that's exactly here. That's theta equals pi. The ground state of the particle on a ring is exactly two-pole degenerate. So the ground state has two states in quantum mechanics. And these two degenerate ground states, you can think about it as a qubit. In fact, this is what people do when they discuss superconducting qubits. It's something very similar to that. So the ground state is a qubit, and these are the states that span the Hilbert space of the ground states. Okay, so this finishes the discussion of the vanishing potential. And now I'll introduce the question that we actually want to solve in this quantum mechanics toy model. And then we will introduce how discrete topology helps to solve this problem. Okay, so this was just, yes. What the ground state is depends on theta indeed. You see that there is level crossing. Every time you hit pi, the ground state changes because of this level crossing. You may remember that there cannot be level crossing in quantum mechanics, but here level crossing does occur because the states 0 and 1 have different momentum. So they are in different sectors. So the crossing is in different charge sectors. Would say that the momentum of the ground state changes with theta. Okay. So what if we put a potential, some arbitrary potential on this ring, and we ask how many ground states are there as a function of the coefficients? This is just the Fourier decomposition of an arbitrary function on the ring. So I'm going to prove to you some result which is extremely difficult to see by direct quantum mechanical computations, which is, it's an example, it's more general, but as an example, I'll prove to you that if you turn on cosine of 2q, so let's say we turn on only cosine of 2q, then this qubit degeneracy survives non-perturbatively for any value of coefficient of the cosine. Now, the first time we've realized that this was somewhat surprising, because we know in quantum mechanics, let me just go to the picture to show you what I mean. I'll just skip a few slides and I'll go back to it. In quantum mechanics, we know that if there are two classical ground states, usually there is an instanton that leaves the degeneracy, and in fact, there is only one true ground state. Here in this problem on the ring, cosine 2q has two minima on the circle, which are at q equals pi over 2 and 3 pi over 2. But it turns out that all the instantons and anti-instantons and multi-instantons all exactly cancel out, and the qubit survives non-perturbatively. So it's an example where the instantons do not leave the degeneracy of the ground state, unlike what we see in graduate school usually. So how do you prove something like that? Of course, you can try to do perturbation theory in cosine of 2q and try to show it perturbatively. But then there are instantons and multi-instantons, and you will not be able to establish it non-perturbatively using standard techniques. So to prove this result, we will introduce some tools from discrete topology. Are there any questions about what the question is? Well, at the one instanton computation clearly shows that it cancels. When you look at more complicated instanton configurations, it's not obvious. There is a Z2 symmetry, but to really show that all the multi-instantons cancel would be not something that I've seen somebody try. But at the one instanton level, there is a discussion in the literature showing that the two configurations cancel. At some point, also, the instanton gas approximation doesn't make sense, as you know. So you can't really go about trying to do that non-perturbatively. You can try to do it for maybe one instanton, two instantons, but at some point, it's not rigorous. Any other questions? Okay. So if you added cosine of q, it would lift the qubit. That's obvious because there is only one classical ground state, and you can make it as deep as you like. So of course, there is only one quantum ground state as well. But cosine 2q would retain the degeneracy because of the cancellations between all the instantons. So let me show you how to prove that non-perturbatively. And the methods have appeared in uncountably many examples in the literature, in magnets, in various gauge theories, in various dimensions. So it's just an example that you can use to build your intuition. So I'm going to go back again to the model with no potential on the ring, understand its symmetries a little bit better, and then we proceed from there. So what are the symmetries of the model with no potential? It's translations along the ring, and that leads to SO2. So there is an SO2 symmetry where you just translate along the ring. But at theta equals 0 and pi, there is another symmetry, which is reflection of the ring, which has q going to minus q. This symmetry just flips the circle, and it's a symmetry at 0 and pi only. Why? Let me go back to show you the Lagrangian. Why the reflection symmetry is only a symmetry in 0 and pi? Look at this term. It's odd under q going to minus q. But theta is 2 pi periodic. So theta equals 0 clearly preserves q going to minus q. But when theta is pi, you take q to minus q, you get pi going to minus pi. But pi and minus pi are the same by the similarity transformation, which shifts theta by 2 pi. So the only cases where q going to minus q is a symmetry is theta equals 0 and pi. So we see that the symmetry of the model is actually O2 when theta is 0 or pi. In other words, it's just SO2. So let's try to understand how the symmetries act on the Hilbert space. When we say that the symmetry is O2, what we really mean, symmetry in quantum mechanics is an operator that is time independent. And you can try to ask, what is the algebra of these operators? So when we say that the symmetry is SO2, what we mean is that this is the algebra of the operators. See this, so reflection, translation, reflection gives you a translation in the opposite direction, and 2 reflections squared to 1. This is the algebra of the operators. But then you have to realize this algebra of operators on the Hilbert space. So these are 2 different things in quantum mechanics. We have to separate these 2 questions. One is how to realize the symmetries on the Hilbert space, and the other is what's the algebra of the operators. When we realize these operators on the Hilbert space, the translations are realized by just conjugating every state with a phase at theta equals 0. We implement the reflection by taking the state n to minus n. But at theta equals pi, while the translations act in the same way, reflections have to take n to minus n plus 1. Why? Remember, for instance, 0 and 1 were degenerate. So you better take 0 to 1, not to 0. Okay? So not to, let's say, minus 1. So this is how these operators are realized on the Hilbert space. So, yes. Yes. So you see, if you try to adopt this, for instance, this convention, then the conjugate of 1 would be minus 1. But 1 and minus 1 are not degenerate, so it wouldn't make sense. So the only way in which it can act is this. The only way in which it can act and be consistent with the O2 multiplication rules is this. Good. So this you can add various space factors. It's not unique. I will show you that there is some phase here that's irreducible. So there is some discrete topology in the space of all the choices. When you ask how to realize operators on the Hilbert space, it's a little ambiguous because you can always multiply by a phase. Sometimes there is a phase that cannot be removed. And I'll show that in this example, there is a phase that cannot be removed, whatever you do. Yes, that's exactly what I'm getting at. So at theta equals pi, at theta equals 0, there is not much to discuss. This action on the states is more or less what you'd expect. It satisfies the rule CVC equals V. The ground state is unique and O2 invariant. But at theta equals pi, this is the best we could do to even write something that makes sense. But it turns out that it doesn't quite satisfy CVC equals V. It satisfies it up to a phase. And now you have to play some game to try to remove this phase. can we change the action of CV on the spaces on the space of states in such a way that this phase would disappear? It turns out that we cannot. I'll show you in a second why. And what happens really is that while the algebra of operators is O2, they're not realizing O2 on the Hilbert space. What they're realizing on the Hilbert space is a double cover of O2, which is called pin2. Okay, so let's try to remove this phase, as Matthias suggested. We can, for instance, instead of acting with translations as we did before, we can define translations in this way. And then we've been able to remove the phase miraculously. But now translations are not 2 pi periodic, and the 2 pi translation is negative 1. So we have some minus sign that just cannot go away. It doesn't matter what you do, you will not be able to define the action of CVC in such a way that they literally on the nose satisfy CVC equals V minus alpha. There will always be some pesky minus sign or some phase that doesn't go away. And that's because this system realizes a short exact sequence where pin2 is a double cover of O2. So that's a projective representation of O2. And it just cannot go, you cannot remove it in the model without the potential. Okay, so this is the point about this little toy example. That's something that Aronov and Bohm, of course, did not say. It's a modern interpretation of some results. So how do we say, what's the jargon? The jargon is to say that the O2 symmetry of the particle on a ring suffers from a 't Hooft anomaly when theta is pi. So we call it a 't Hooft anomaly nowadays. And the ground state is in a projective representation of O2, which is called pin2. And the most natural choice for how you act with with C and V on the ground state is the one here, where U2 pi is minus 1. And that means really that the qubit is a fermion. So when you take the qubit states 2 pi around, you pick up a minus sign. So you can think about it as the simplest example of boson-fermion duality. Maybe it's a warm-up to the next lecture. It's the simplest example of boson-fermion duality because we started from a particle on the ring, but when the flux was a half, we got a qubit, which is a fermion. And in fact, you can show that it's really dual in this stupid model. So you can show you can analyze how the symmetries act on the free complex fermion in quantum mechanics, and you can really match the anomalies and everything. So it's a silly little boson-fermion duality. Okay, so we're dealing. Yes. I mean, for the ground state, it's an infrared duality. The ground state realizes the symmetries in the exact same way, and perturbations can be mapped and so on. So how do we go back to this cosine problem? So the first insight is that we dealt with O2, but we didn't need O2. You could preserve just a Z2 times Z2 subgroup of O2, which includes translations by pi and reflections. And Z2 times Z2 still has a projective representation. It still has a Z2 cover, a short exact sequence, given by this. So V and C are Z2 generators, but their algebra has a phase where eta is minus 1. So eta is minus 1 for theta equals pi, and eta is plus 1 for theta equals 0, saying that there is anomaly at theta equals pi, but there is no anomaly at theta equals 0. So we see a double cover of Z2 times Z2. This particular double cover is the dihedral group. So you could say that the Hilbert space realizes the dihedral group but the algebra of operators is Z2 times Z2. Okay. So if you just preserve Z2 times Z2, you're in great shape, because now you can add potentials that preserve Z2 times Z2 and nothing will change. Because this minus sign is not something that you can change continuously. This short exact sequence, that's probably the central idea that I should emphasize. Once you find that there is a central extension or a short exact sequence, you cannot make it disappear once you add interactions. It's a discrete object, and it cannot change discontinuously to something, because this eta is either 1 or minus 1. Maybe it's more clear in this slide. This eta is either 1 or minus 1. If you found that it's minus 1 in the free theory, it cannot turn to be plus 1 when you add a coupling which is 10 to the minus 100. So therefore, even for finite coupling, eta has to remain exactly -1. And therefore, whatever potential you add, you'll have to have a projective representation of O2 or Z2 times Z2. And projective representations of Z2 times Z2 cannot be one-dimensional. Because if it's a one-dimensional representation, then eta is +1. You cannot realize this algebra. I should say that you cannot realize this algebra of charges with eta equals -1 on a one-dimensional Hilbert space. Because on a one-dimensional Hilbert space, whatever you do, eta will be +1. So therefore, we prove that there is a qubit even with a cosine 2q potential. And in fact, cosine of 4q, cosine of 6q, whatever you want, of this form will preserve the qubit. So the qubit is very robust if you can preserve Z2 times Z2. Are there any questions about this discussion? Okay. So I already explained that this is a little different from the intuition about instant thoughts. Now we're getting to Yang-Mills theory, and we'll use similar ideas to try to understand the phases of Yang-Mills theory. So let me review the classical counterpart. I'll just follow the same steps. Some of the things will be slightly more complicated, but you'll see that we can literally follow the same steps to derive some results about Yang-Mills theory. So just to remind, Yang-Mills theory is the field theory of a SUN connection and by Hermitian matrices, in other words. So you define the field strengths like that, and you have a classical action like that. And these are the classical equations of motion. And of course, there's a lot of discussion of these classical equations of motion and interesting solutions that will not concern us today. So this theory can be viewed as a nonlinear version of Maxwell's theory. And the crucial difference from Maxwell's theory is that the electric and magnetic fields are also charged. So they are themselves charged under the connection. They're in the adjoint representation. And this leads to an important difference from Maxwell's theory. And this will be perhaps the next central idea in this talk. In Maxwell's theory, we have a Gauss law. The Gauss law says that if you surround an external charge, in pure Maxwell theory, without dynamical charges, if you surround an electric charge with a surface and you integrate the electric field, the answer is independent of the size or shape of the surface. That's Gauss's law. In Yang-Mills theory, you cannot do that, because in Yang-Mills theory, the gluons themselves carry SUN charges. So if you try to build a surface surrounding some external charge in Yang-Mills theory, you will not be able to measure the charge exactly, but you will be able to measure the charge mod n. And that's an interesting conservation law in Yang-Mills theory, which is nowadays called one-form symmetry. So the point is that if you put a probe charge into Yang-Mills theory, let's say in the fundamental representation or the representation with two boxes, let's say the symmetric representation, and you try to measure the Gauss law, integrate the electric field, you will not have a universal answer to that question, but it will be universal mod n. Because all the gluons can do is to dress the source, which is in the representation R, with adjoint indices. So the number of boxes mod n in the Yang tableau cannot change. So Yang-Mills theory has a Zn symmetry. It's difficult to write the explicit expression for the conserved charge. Unlike in Maxwell theory, where we just integrate the electric field, here it's difficult to write an explicit expression because it's a discrete symmetry. So for discrete symmetries, we usually don't have a very explicit Lagrangian description. But there is a Zn symmetry, and in Maxwell theory, it's U1. So that's why we have a continuous expression. Here it's just Zn. Okay? So this symmetry is called one-form symmetry. It's a discrete version of Gauss's law. This Zn symmetry, just to put it in your head, is going to be analogous to translations on the circle. So on the circle, we had the SO2 symmetry when there were no interactions. Mathematically, this Zn symmetry will be essentially identical to a subgroup of translations on the circle by n 1 over n, by steps of unit 1 over n. Okay, so the Zn should be interpreted as a subgroup of SO2 as far as the mathematics will be concerned. So now we need to discuss the analog of this Q dot. Sorry, this should be dt. It's a typo, I'm sorry. dt Q dot. This is this term that we can add to the classical Lagrangian that has no impact on classical physics, but is important quantum mechanically. Similarly, in Yang-Mills theory, we have a total derivative term, which is the second Chern class, trace f wedge f, which we can integrate over space-time, and it's a total derivative in classical physics and does not do anything. And that's why people that analyze Yang-Mills theory in mathematics often ignore this term, and they just study the Yang-Mills equation. They completely ignore the theta angle because it doesn't do anything classically. But quantum mechanically, it plays a crucial role, of course, as in the particle on the ring example. So we can add a theta angle, and there is a similarity transformation, exactly like in the particle on the ring story, where theta goes to theta plus 2 pi. So let me show you how the similarity transformation is implemented. The similarity transformation is implemented by an interesting unitary operator, which is integrated on the 3 manifold. So when we conjugate a Hamiltonian, we conjugate it by a unitary operator that is at fixed time. So in the Hamiltonian formalism of Yang-Mills theory, we can conjugate the Hamiltonian by this interesting unitary operator, which is the exponential of the Chern-Simons term. And if we conjugate the Hamiltonian with this guy, you can see explicitly that theta is going to be shifted by 2 pi. So we have an explicit expression for the unitary that shifts theta by 2 pi, and therefore theta is 2 pi periodic, exactly like for the Aronoff-Bohm problem. And indeed, also as in the Aronoff-Bohm problem, theta equals 0 and theta equals pi are special. This is the analog of the reflection symmetry that we had on the circle. The analog here is the CP symmetry, which is charge conjugation followed by parity, or equivalently, it's time reversal symmetry. By CPT theorem, you can discuss either CP or T, pretty much the same. So theta equals pi and theta equals 0 are special because they're both time reversals invariant. And okay, are there any questions about this just review of Yang-Mills theory? This is unitary. It's a unitary. CP is unitary, T is anti-unitary, and CPT is anti-unitary. If you don't want to ever discuss anti-unitaries, discuss CP. So the analog of the Z2 reflections is CP, it's unitary. The analog of the conjugation is this unitary operator U. And the analog of translations is the Zn1 from symmetry, which is the Gauss law, the discrete version of Gauss's law. Okay, so this is the analogy with the circle. Okay, so let's summarize the symmetry group. At theta equals 0 and pi in Yang-Mills theory, we have time reversal symmetry. I switched to the anti-unitary but it doesn't matter. I could use Z2CP. We have time reversal symmetry and the Zn1 form symmetry. And exactly like in the particle on the ring, it turns out that there is a 't Hooft anomaly. So that means that if you study the theory on some compact manifolds, there will be projective representations for the full ground state of Yang-Mills theory. So in the particle on the ring example, I explicitly derived the anomaly for you by setting the potential to vanish, solving the free theory, and realizing the charges on the Hilbert space. Here, this cannot be done. I cannot get rid of the potential. I cannot make Yang-Mills theory into a free theory. But the anomaly can be derived in a similar way. You can derive the anomaly in a similar way by some similar tricks. And this anomaly has far-reaching consequences, and I'm going to spend the next couple of minutes explaining what it implies for the dynamics of Yang-Mills theory, confinement, deconfinement, and time reversal symmetry. So the first consequence is if you put theta equals pi in Yang-Mills theory, we have an analog of the qubit. So Yang-Mills theory at theta equals pi cannot have a trivial gap vacuum. It has to have at least 2 ground states. Now, in recent years, people have kind of saw that more or less explicitly by deforming Yang-Mills theory by adding various matter fields and going to weakly coupled limits. And you can really see that there are 2 ground states. But that should still be true, at least for SUN with large enough n. That is what the anomaly would imply, that there are 2 ground states at theta equals pi. And time reversal symmetry is spontaneously broken. So theta equals pi Yang-Mills theory is time reversal invariant but the ground state breaks it spontaneously. And one thing you can ask whenever there is a spontaneous symmetry breaking, you can ask, what happens if I construct a domain wall going from one vacuum of Yang-Mills theory to the other vacuum of Yang-Mills theory at theta equals pi? So there's some domain wall. And the anomaly has a very interesting prediction, which is that on the domain wall, there is going to be a topological field theory with deconfined fractional spin particles. So maybe I have a picture in the next slide. Uh, I'll explain what happens on the domain wall. So we have two vacua in Yang-Mills theory at theta equals pi. If we construct an interface between them, the prediction of this anomaly is that quarks are liberated. First of all, the quarks in the bulk, which are confined, they become deconfined. And secondly, they become anyons with fractional spin and for other fractional quantum numbers. So the interface has deconfined quarks, and that's my attempt to explain what's going on. So we have one vacuum of Yang-Mills theory here, another vacuum of Yang-Mills theory on the other side. And it turns out that on the interface, if you localize the quarks on the interface, they should have non-trivial braiding. So, and that means that they're deconfined. And furthermore, they have fractional spin. So the quarks in Yang-Mills theory could be some heavy particles of spin a half, but on the interface, they have fractional spin, which is 1/2n plus a half mod 1. And furthermore, they're deconfined. So the flux tube disappears. This has not been seen yet in simulations, but that's a very striking prediction that confinement disappears on the interface. Yeah, external quarks. So this, thank you very much for the, I should have said, I'm discussing pure Yang-Mills theory. In pure Yang-Mills theory, we don't have any quarks, but the thought experiment that we're doing, the Gedanken experiment, is that we're adding some external particles in some representation R, and they're confined. We see that in nature pretty much. We see that there is confinement. So the prediction is that these external particles become deconfined on the interface. So if you place external quarks on the interface, there is no flux tube. There is a very small force, if any, between the quarks. Yes. So right. So the quark lines in the bulk, there are some external particles. Maybe there are spin half fermions which are heavy. Maybe there are spinless bosons which are heavy. But when you bring them to the interface, they acquire fractional spin and they become deconfined. This all is implied by the anomaly. I think if you put them on two sides, if you put one here and the conjugate representation here, first of all, it's a good. I think that there will be a flux tube that goes here. The flux tube would lose its tension in this small region, and then the flux tube would come out of here. So I don't think you'll see something remarkable if you did that simulation. To see something remarkable, you have to put them on the surface, and then you will see that the linear force disappears. Yes. So you could. That's what I told the Kolya, that indeed you could have the flux tube just terminate here. The end of the flux tube can be viewed as a quark, and that quark, instead of having linear force, could just spread around. Yeah. So this is the prediction. It has not been seen yet on the computer. You can think about it as an intriguing connection. Yeah. 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 So this scenario here, where we assume that the anomaly in time reversal symmetry and one form symmetry is saturated by two ground states breaking time reversal symmetry spontaneously is not proven. There is an anomaly. The ground state cannot be just a single confined vacuum, like the Millennium Prize is for. So it has to be more complicated. This is a minimal scenario. Whether this is actually what happens in SU2 or even SU3, we don't know. It could be a gap. As far as we know, theta equals pi could be gapless. This happens in some variants of this discussion, like the Haldane chain. Sometimes it's gapless for SU2 and gap for SU3. And this is just the minimal thing that we believe is true for SU4, SU5, maybe SU3, but we don't know yet. Well, this shows that the millennium question is not true at theta equals pi. So there is not, yeah, it just, a negative solution, yes. No, if you're just interested in a negative solution, that's already finished. That already proves that the Yang-Mills theory cannot be in a single confined gap vacuum. There is no gap here. There are two vacua. I think the Millennium Prize must have meant theta equals 0, though they didn't specify. It doesn't mention, so yeah, it's not. It's okay. That's a excellent question. So the question is if there is an anomaly for all n or only even n. So there is an anomaly only strictly speaking for even n. There is no non-trivial projective representation for odd n. But there is an extension of the notion of anomaly, which is a higher Berry phase. It's what people sometimes call an anomaly in the space of theories. It's a slightly higher version of the anomaly concept. And that exists for any value of n. Yes, that extended anomaly has slightly weaker consequences. It means that there cannot be a trivial gap confined vacuum at all theta. There has to be at least one theta for which there is something interesting. But it doesn't say that it has to be theta equals pi. But for even values of n, you know that it's got to be at theta equals pi. Yeah, so we don't know that this is really what happens in Yang-Mills theory. It's just the simplest thing that's consistent with the anomaly. In ADS-CFT constructions, like Witten's model, that's what happens. That we check. Okay. So this story is kind of the beginning of an interesting connection between the dynamics of four-dimensional theory and three-dimensional theories. There has been a lot of work in recent years about connecting four-dimensional dynamics to three-dimensional dynamics, sometimes through circle compactifications. This is a different way. You construct a domain wall, and the physics on the interface turns out to have interesting Chern-Simons-like dynamics with deconfined quarks, some topological filter is coupled to matter. You can generate very interesting three-dimensional physics on interfaces. Even in QCD with quarks, this still works. You get very interesting theories on the interfaces. And there's been hundreds of papers on that kind of thing. Okay, now I want to show you something that is maybe somewhat less familiar. Usually anomalies have no implications whatsoever at finite temperature. That's the law in the field that Hooft anomalies constrain the ground state at 0 temperature. But if you crank up the temperature, there is no consequences to the Hooft anomalies. Indeed, the axial anomaly in QED, for instance, has somewhat weak or implications at finite temperature for transport, but nothing remarkable. This example is different. In this example, there are far-reaching implications also at finite temperature. So it turns out that this is the axis of temperature, and this is the theta angle. So it turns out that the anomaly leads to the following constraint. I'm just going to summarize what the constraint is. The anomaly implies that at any temperature whatsoever, you cannot be in a gapped vacuum, in a confined vacuum where time reversal symmetry is restored. So that cannot happen at any temperature. There cannot, so that's the theta equals pi, of course. So let me summarize again. The anomaly implies that the theta equals pi, you cannot have a situation where the theory is confined and time reversal symmetric and gap. And that's true at any temperature. And this implies something interesting. So we know already the time reversal symmetry is broken at theta equals pi, at least for some large enough n in SUN gauge theory. And we also know that symmetries are restored at high temperatures. There is a very famous folklore saying that all the symmetries are restored at high enough temperatures. So we expect that at some high enough temperature, the time reversal symmetry or the CP symmetry will be restored. So this line is a first order transition from, this line is the first order transition due to the appearance of two degenerate vacua, which break time reversal symmetry. So that's like the Ising Z2. And that line has to terminate. Another interesting transition is between confinement and deconfinement. We know that Yang-Mills theory is confined at low temperatures, but deconfined at higher temperatures. So what the anomaly implies is that it cannot be that time reversal symmetry would be restored before you hit the deconfinement transition. So it cannot be that this line will terminate before the deconfinement transition, because then there would be a region where the anomaly is not satisfied. So this inequality follows from the anomaly, and it implies that this deconfinement transition has to be crossed by the CP transition. And furthermore, it's very natural to conjecture that this line ends with the 3D Ising model, because you have to restore Z2 symmetry at finite temperature. And the most natural way to do that is with the Ising three-dimensional Ising field theory. Okay, so we, second please. There is latent heat here. So see, the two vacua are degenerate at theta equals pi. If you go to theta equals pi plus 0.01, this goes up a little bit and this goes down. If you go the other way, then they flip. Okay, so it's a standard first order phase transition if you go in the theta angle direction. As you heat up, the two vacua should come together and eventually merge into one, and that should be a 3D Ising phase transition with the 3D Ising critical exponents. Yes, so yeah, so I think the most, oh, sorry, I'm going back. The most reasonable, the simplest conjecture for the phase diagram that should hold at large n, maybe, we don't know, but is that this is first order, it ends at the second order 3D Ising because it has to end at the second order transition. And this is first order. This is the simplest scenario that's possible. Already for SU2 gauge theory, this scenario cannot be true because we know that this line is second order in SU2 gauge theory. So therefore, this has to be a little bit more complicated. And in the original paper, we had a whole section trying to understand how can this cross. Because if this is second order, they cannot just cross like that. You have to have some more interesting criticality that involves some O2 critical models. Hmm? When you look at the Witten model or some Maldacena-Nunez type models, this point where the 3D Ising model appears happens to exactly coincide with the deconfinement phase transition. So time reversal symmetry is restored exactly together with deconfinement. Witten model is just like it's like a picture for what Yang-Mills theory is, where you interpret it in ADS 5 times SY F5 with anti-periodic boundary conditions. It's just a picture. But in that model, the two transitions exactly coincide here. So time reversal symmetry is restored exactly when deconfinement sets in. Recent numerical simulations in SU3, which you may or may not track, suggest that in SU3, time reversal symmetry is restored after the deconfinement transition. So no, we don't know if they happen together or there is a strict inequality. The anomaly implies only a weak inequality, not a strict inequality. There is recent progress on simulating gauge theories with theta angles, where you go to complex theta angles and try to analytically continue. You go to purely imaginary theta angles and then try to analytically continue. And also, of course, there's a huge amount of work on realizing gauge theories with qubits. So maybe that one day will allow to simulate this, DMRG. So we're not sure what the phase diagram is in the SU2 case. Maybe even it's fair to say we don't know what it is for the SUN case, but that's the most likely scenario. Are there any final questions before I summarize? Oh, I had one more comment before I summarize for just the connections to nature. Yeah. I don't impose. So you see, all you can derive is a non-perturbative constraint that there is an anomaly. So that's the rigorous piece. That there is an anomaly, the ground state cannot be trivial, confined, like in the Millennium Prize, okay? That you can derive. The rest are attempts to understand what is the ground state that could satisfy the anomaly. And all I was saying that the simplest case, the simplest scenario is spontaneous breaking of time reversal symmetry. And this phase diagram at finite temperature. This is just the simplest thing you can cook up that that satisfies the anomaly. It doesn't mean that it's what happens in SU2. It doesn't even mean that that's what happens in SU100. But that's what happens in some holographic avatars of Yang-Mills theory. And that's what happens in some deformed Yang-Mills theory by adjoint scalars, for instance, that Mithat Unsal and his collaborators analyzed with some double trace deformations. So we know some examples that actually give this answer. We don't know that this is what SU and Yang-Mills theory will give. Yeah. Which duality? Yes, that duality is an infrared duality. So what do I mean by duality? I mean that there's Yang-Mills theory in 4 dimensions, and then there is an interface. And the statement is that the interface has interesting Chern-Simons matter theory. So some anyons which are fluctuating and dynamical. That statement is exact. And then the question is, what does the interface do at low energies? Because sometimes sometimes Chern-Simons matter theory has complicated dynamics in its own right. But yeah, you can sometimes answer these questions using these ideas. I just don't have time to go into that today. I just wanted to finish with implications for nature. One of the biggest problems in nature is, of course, to explain the origin of time reversal symmetry in the standard model. We know that the standard model has a time reversal symmetry violation. And the question is, where is it coming from? This gives a very interesting scenario. Maybe instead of the dark matter being one particle, maybe dark matter is a theta equals pi gauge theory. So the whole model is time reversal invariant to begin with, but then time reversal symmetry is broken spontaneously in the hidden sector, and it's communicated to the visible quark masses through some mediators. That's something that's a variant of what you might call the Nelson-Barr mechanism for CP violation. And I think it's a viable idea. It's an interesting way to induce time reversal symmetry in the quarks. So that was my comment about the possible connections to nature, like the particle physics. And I'll just summarize to say that the ideas of topology that I alluded to here have, of course, featured in the works of many people in the audience, and they have had striking applications in the last 10 years, I would say, for QCD and many generalizations in various dimensions, 1 plus 1, 2 plus 1, 3 plus 1, for nail VBS transitions, antiferromagnets, lattice models of this type. There has been an explosion of exact results due to discrete anomalies, like what I explained today, for Chern-Simons matter theories, for sigma models, and many, many others. So these methods using topology in the space of theories, or topology in the space of theories and 't Hooft anomalies, have been very fruitful in the last decade. It's a window into non-perturbative physics. It leads sometimes to concrete, verifiable predictions. The mathematics is interesting. It touches upon cutting-edge algebraic geometry to really write the formulas associated to this anomaly with time reversal symmetry and one-form symmetry. You have to, it's a very advanced mathematical task, and people have done it only recently in the last couple of years. And there are many applications to dualities and domain walls and interfaces and thermal physics and so on and so forth. So, okay, thank you very much.
Hey, thanks for being perfectly on time. There were already interesting discussions. More questions? Yeah, please.
Just a second, maybe microphone?
About if we get one form symmetry and get something like one form magnetic form symmetry, and there should be still some anomaly at the
Yes.
pi equal to pi. So what is the domain of theory of the PSUN gauge theory?
Yes, that's an excellent question. So the question is, what happens if we try to gauge the one-form symmetry? And how do we, there's some anomaly and so on and so forth. This was studied in the literature. There are many papers on this question of what happens to the anomaly after you gauge the one-form symmetry. It turns out that you get somewhat interesting structures. In many of these cases, you get two groups. Sometimes you get non-invertible symmetries. It depends what the anomaly exactly is and which symmetry gauge. You can get various interesting structures. In this particular case, if you gauge the ZN one-form symmetry and you get PSUN gauge theory, there is no more time reversal symmetry at theta equals pi. So in PSUN gauge theory, theta equals pi has no time reversal symmetry because the periodicity of the theta angle in PSUN gauge theory is not 2 pi, but 2 pi n. But still, 2 pi is a special point because you get some interesting higher group somehow. And it turns out that there's still two ground states in PSUN gauge theory. But one of them has a topological field theory. So in one of them, let's say this one, there is a Z2 gauge theory, a low energy topological field theory. And the other one doesn't have a topological field theory. So there is no time reversal symmetry, but you get something else instead. You get two vacua with one of them having a Z2 gauge theory. Okay? So this was analyzed in great detail. That's more or less what happens, what I just told you. And if you go to Seiberg-Witten theory, you can somehow see that there is literature about SU2 Seiberg-Witten theory versus SO3, and if you deform it appropriately to break the supersymmetry and to make it in the same universality class as Yang-Mills theory, you will see that indeed the Witten index of SO3 gauge theory is 3, if I remember correctly. I hope I'm not saying something wrong. While for SU2 it's 2. And that can be traced to the fact that one vacuum has a Z2 gauge theory. So on a circle, it has two vacua, and the other one has one.
Yeah. Any more questions? Okay, if not, please.
A naive question for when you increase the temperature, you get the deconfinement and confinement phase transition. Is there insight why for between NX2 and NX3 there is the order change from first to second, and insights?
Yeah, so there is an old paper from the 80s. Sorry, I'll go back to that. You can ask why this transition is continuous for SU2 and discontinuous for SU3 and above. There is an old paper by Svetitsky and Yaffe from around 83, I think, maybe Svetitsky Yaffe, where they analyzed using Landau-Ginzburg ideas, they analyzed the possible order of this phase transition. And they have an argument from naturality that as for SU2 it's natural that it will be second order, while for SU3 and higher it's not natural. We don't have some new insight into that. The most important question here is why in the large N limit, this phase transition coincides with that one in temperature. Why the confinement happens together with time reversal symmetry restoration? That's perhaps the most pressing question about the large N limit of SU and Yang-Mills theory. We see that happens in ADS-CFT, and the question is whether it's a general fact that will also be true in Yang-Mills theory. Maybe this gap goes to 0 when N goes to infinity.
Questions?
Thank you.
If not, let's thank